If you are watching this video for the first time, make sure you are subscribing to Untitled Academy. Once you click on the subscribe button, you will see a bell icon. If you click on that bell and click on all, you will get to know whenever I upload a video. This will send you a notification. Hello everyone, welcome to Untitled Academy. I am Untitled here to teach the very first chapter of 10th class mathematics, which is real numbers. Today I am going to explain the introduction and the corresponding exercises of real numbers, the very first chapter. Even before getting into this chapter, let us brush up our number system in a while, okay? When I talk about number system, what is it? Number system. How many kinds of numbers which we have learned from so far? First thing we have learned is natural numbers. What are natural numbers? Natural numbers are nothing but the numbers which get started from 1, 2, 3 and it goes on. Right? Next thing that we are going to discuss is about whole numbers. Whole numbers. Where does the whole number start from? Whole number starts from 0. 0, 1, 2, 3 and it goes on. So initially when natural numbers were natural numbers were invented, and then in order to figure out 1, 0, we needed a 0. That is when we came up with the concept of whole numbers. And then we have even numbers. What are even numbers? Which are divisible by 2. 2, 4, 6, 8 and so on. And we have odd numbers which are not divisible by 2, 1, which are in the form of 2n plus 1. 1, 3, 5, 7 and so on. Alright. Then we have prime numbers. Prime numbers are nothing but which are divisible by 1 and itself. 2, 3, 5, 7, 11 and the series goes on. And then we have composite numbers. Composite numbers. What are composite numbers? Composite numbers are nothing but which are divisible by 1 themselves and by some other numbers as well, which are nothing but everything like 4, 6, 8 and it goes on. Alright. And then we have rational numbers. What are these? Rational numbers. So what are rational numbers? Rational numbers are the numbers which can be expressed in the form of P by Q. Nothing but the fractional part. Okay? Rational numbers are the numbers which can be expressed in the form of P by Q. Again, in rational numbers, we have two types. Okay? One is terminating. What is terminating? If you take a fraction, suppose 25 by 4. Let me give you an example of 25 by 4. What happens for 25 by 4? This is nothing but 4 6 are 24. Again, if you take the point, it goes till 6.25. Alright? So, what is this? The result of this is terminating after a definite decimal expansion. Isn't it? The result is not going beyond that. At 5, the fraction is done. The remainder is 0. Alright? That is what is this is terminating. Terminating is nothing but this particular expression which is expressed in the form of P by Q. The rational number is going to terminate after a definite decimal expansion. That is first type. Then we have non-terminating. Non-terminating. So consider a fraction of 10 by 3. What happens? It is like 3.3333333. It goes on. This is non-terminating and the 3 is repeating. The second type is non-terminating and repeating. For all the numbers, I just gave a simple explanation. And why am I stressing on rational numbers, terminating, non-terminating and repeating all this? You will get to know as we go on. So please do watch this video till the end. Okay. So rational numbers which are expressed in the form of p by q, within that there are two kinds. One is the terminating decimal, which meant the decimal expansion is going to end after a particular point, and the other is non-terminating, and when it is non-terminating, the decimal point after that, the whatever the value that we are getting is supposed to repeat. These are the two things. Now when I said non-terminating and repeating, now we should get it out. Is there any type which is non-terminating and non-repeating? Yes, there is, but that is known as irrational number. They are named as irrational numbers. So what are irrational numbers? They are also the fractions which can be expressed in the form of p by q, but they are non-terminating. They doesn't end, and they don't even repeat. Non-terminating and non-repeating. Alright, what are the examples of this? The familiar pi, which is nothing but 22 by 7 or 1 by 7. This goes on these values, root 2, root 3, etc. Alright. So within the number system, we have discussed natural numbers, whole numbers, even numbers, odd numbers, prime numbers, composite numbers, rational numbers, and irrational numbers. So far we have discussed only positive numbers. We forgot one thing, which is integers. What are integers? Integers are nothing but which begins from the negative side. Say for suppose -3, -2, -1, 0, 1, 2, 3 and so on. This is the integer series. The ones which are in negative form, which are having minus, are known as negative integers, and the ones which are positive, I mean after 0, they are known as positive integers. Alright, so far and then we have rational numbers, irrational numbers. So now coming to the concept of real numbers. What are real numbers? Now that Anantalakshmi has explained all the number system, now let us see what exactly is real numbers is. So what is real numbers? It is nothing but rational numbers and irrational numbers. When you mix them into a set, they are known as real numbers. Alright, when I said rational numbers which are in form p by q, now when I say a number is 1, what is the denominator in it? 1, isn't it? Can 2 be expressed as a fraction? Yes, the denominator will be 1. Can 3 be expressed as a fraction? Yes, the denominator will be 1. So for all the natural numbers, whole numbers, even numbers, odd numbers, prime numbers, composite numbers, integers, all the denominators are 1, which meant they can also be expressed in the form of p by q. So all the sets which we have discussed just before the rational numbers comes into the rational number set. The natural numbers, whole numbers, even, odd, prime, composite, integers, everybody is going to come and sit in the set of rational numbers. And we have non-terminating, non-repeating, irrational numbers. Alright. So all these numbers include the concept of real numbers. Now that we have expanded this to this much, and all of them coming into a single picture, which is our first chapter, real numbers. So this is the introduction of real numbers. Let's discuss the first concept in the chapter, real numbers. Alright, so let's get to the concept. So let's get to the concept, Euclid's division algorithm. Euclid's division algorithm, the very first concept in our first chapter. Alright, so before we get on to this algorithm, the terminology, like what is an algorithm, is everybody aware of this algorithm? So say for suppose, let me give you an example. If somebody asks you to prepare tea, how do you prepare tea? You say that I'll lighten the stove first, take the milk into a container, and then put it on the stove, and then I add some sugar, tea dust and all. This is what you will be telling, right? The step-by-step procedure that you tell or write, that is needed to do any process is known as algorithm. Algorithm is nothing but a step-by-step procedure that is to be followed to achieve something. Alright, that is what algorithm is. Division algorithm. Earlier in our earlier classes, say for suppose 6th, 7th or 8th, we are aware of one division formula, which is, let me consider like 10 divided by 2. 10, okay, 10 divided by 2. Alright, what happens? 2 5s are 10 and the result is 0. What is the operation that will be done here? This is a subtraction operation. Now, so what is this 2 called as? This is nothing but the divisor. What is this? Divisor. What is 10 called as? Dividend. You must be aware of this, but since this is in the introduction part, I am just, some people may get confused to divisor and dividend. So let me make clear this. Okay, this is what is 5. This is known as quotient. What is 0? This is nothing but remainder. So we have 4 elements when we perform division. One is divisor and the other is dividend. The thing which we write here is known as quotient and the other one is remainder. Alright, we had a formula called dividend is equal to divisor into quotient plus remainder. This is a formula which we have. Alright, then we have Euclid's division lemma. If you read out the textbook, you will get to read a word called lemma. What is lemma? Lemma seems to be a new word, right? What do we say? Okay, the sun rises in the east, which is a already proved fact. Depending upon that, can I say the sun sets in the west? Yes, because I am saying that the sun sets in the west. That is because the sun rises in the east. I am concluding the second statement depending upon the first statement. Alright, if you use an existing proven algorithm or any formula to make a statement, then that is known as lemma. This Euclid's division lemma is based on the division algorithm. Let us see what Euclid is saying about the division algorithm using his lemma. So what he says is, he considers it like, let me give you an example. Like, he considers the dividend to be C, an alphabet C, okay, and then divisor to be D, quotient to be Q, remainder to be R. So what is our division algorithm? Division algorithm is dividend is equal to divisor into quotient plus remainder. So in these letters, can we express it? So what does it make? C is equal to DQ plus R. Isn't it the same as division algorithm? Dividend is equal to divisor into quotient plus remainder. So within his lemma, what he is trying to say is the remainder is less than the divisor. Okay, less than the divisor. 0 is less than divisor, right? Remainder is always less than the divisor. Okay, and it may be equal to 0. When the division is completely done, the remainder is 0. Alright, 0 less than or equal to remainder, and remainder is less than the divisor. Isn't it true? Yes, right? This is what he explains. Euclid's division lemma is used to figure out HCF. HCF is nothing but highest common factor. Alright, we will discuss this in detail. So first understand this concept of his lemma. What is he saying? He is just saying whatever we have in the division formula itself. Dividend is equal to divisor into quotient plus remainder. But in order to figure out HCF, he is mentioning that the remainder is always less than the divisor, and remainder may be also equal to 0. This is the first thing. Okay. Now let us consider an example of 8 and 12. 8 and 12. If I ask you to figure out the highest common factor of both 8 and 12, what are the factors of 8? You tell me. 1 is a factor of 8, 2 is a factor of 8, 4, then 4 2s are 8, and 8 is a factor of 8, right? 4 factors we have. And what about 12? 1, 2, 3, 4, 6, and 12. So highest common factor, when I say HCF of 8 and 12, what are common in between these two? In between the factors, 1 is common, 2 is common, 4 is common. Among the common factors, they want the highest one. So what is the highest one? 4. Isn't it? The HCF of 8 and 12 as per our regular process becomes 4. Let us solve this by using Euclid's division lemma. So within this lemma, I just have mentioned the first point. There are 2 more points to be mentioned. So what he says is, he uses the same division algorithm. 8 ones are 8. What is the remainder? We get subtraction, we get 4. Now what he says is, in order to obtain the HCF, if the remainder is not equal to 0, then we are going to use this remainder to divide the divisor. So this guy is going to come here. Okay. If the remainder is not 0, then we are using this number to divide the divisor. Alright. Do not get confused. If the remainder is 0, well and good. If it is not, then we are going to use this number to divide the divisor. So divisor is going to come into picture. Then 4 2s are 8. And the divisor with which we got the remainder is 0 is said to be the HCF of those two numbers. What is the HCF as per our regular process for 8 and 12? It is 4. What is the HCF as per the Euclid's division lemma? It is 4. So this is Euclid's division lemma. So for now the question comes up, why are we trying to explain this? Why don't we have it? Because this is quite simple, right? Now figure out the HC of 2002 and 1048. What will you do? What will you do? You sit and keep on writing the factors? It is quite impossible, right? It takes hell lot of time. For those kind of things, we have Euclid's division lemma. Okay. Now, so whatever we have done, if now that we got the remainder, when we divide the divisor with 4, if this remainder is also not going to be 0, then what are we going to do? Then with this remainder, we are going to get this divisor here and start dividing this. So this process will repeat until the remainder is 0. Alright, let me make it more clear. There are 3 simple steps in Euclid's division lemma. The first thing is the division algorithm. C is equal to dq plus r, where 0 is less than or equal to r less than divisor, which meant remainder can be either 0 or it is always less than the divisor. That is first point. Now, the second point is, this is the first point. Now, what is the second point? If the remainder is not equal to 0, then what are we going to do? Then we divide what? We divide d with r. Is it what? We divided the divisor with remainder. Okay. What is step 3? Continue the process until remainder is 0. Alright, so there is nothing much in Euclid's division lemma. Do not get scared by listening to the name. Lemma is nothing but if you are trying to prove something by taking which is already proved, which is nothing but the division algorithm, the division formula which we have took and used the same thing to figure out the HCF. Alright, I guess it is clear so far. This is about the Euclid's division lemma. Now, before we get on to the exercise, I suggest you guys to go through the examples that are based on Euclid's division lemma so that we could jump into the exercise and start solving. Alright, so let's jump into the exercise part. Yeah. So let's solve the exercise part. Here I am ready with the problem already listed. I'm trying to solve the first bit of first problem using Euclid's algorithm to find the HCF. Alright, so far we have discussed what is Euclid's algorithm and how do we solve it, right? So let's get started. For the solution, in 900 and 270, which is the smaller number 270, right? We have to consider the smaller number as divisor and the bigger number as dividend. Alright, always remember this, the smaller number is divisor and the bigger number is dividend. Okay, now 270, okay, 27, right? 272s are 540, 273s are, let us do the multiplication and figure this out. 3 zeros are 0, 3 sevens are 21, 3 twos are 6, 7, 8. Okay, if I do 274s, it will be more than 900. So I'm going with this 8, 1, 0. Now do the subtraction part. 0 minus 0 is 0. 10 minus 1 is 9. Now the remainder is not 0. Now as per Euclid's division lemma, what are we supposed to do? Use this remainder to divide the divisor. Alright. So I am using 90 to divide this particular divisor. Now 93s are 9 3s are 27, right? 270. And hence the remainder is 0. So what is the HCF of 900 and 270? It is nothing but 90. Alright. Always make sure to put the solution into a box because that grabs attention. Alright. So let us solve the next one, 196 and 38220. Alright. So what is the smaller number? 196, right? 196 and bigger number should be dividend 38220. Okay, 196 ones are 196. Now this is going to be 12 and this is going to be 7 and this is going to be 2. All right, so 12 minus 6 is 6. This is going to be 8 and 2 minus 1 is 1. All right, so what happens now? If there is no other number next to this 382, then we could use this number to divide this number, but the division is not completely done, right? So get those numbers here. 18620. Let me try what is 196 nines. 9 6 54, 9 9s are 81, 86, 9 1s are 9, and this is going to be 1764. Okay, now this is 9s. This is 1, 7, 6 and 4. All right, now do the subtraction part. This is 12 minus 4 is 8, 15 minus 6 is 9, and right, this is, now get the 0 downstairs. This is going to become 980. Now let me try 196 5s are 5 6 are 30, 5 9s are 45, 48, 5 1s are 5. Okay, all right, so 196 5s are 980, and when we do the subtraction, this is 0. So what is the HCF of this? Okay, so do not forget that when the whatever the dividend that is given to us, when this is a bigger number, we have to make sure all the digits of it are considered during the division, because first thing what we have done is 196. When it got divided, when 196 ones are 196, we have two more digits which were left. So I took them down and completed the division. By the time I completed the division, I got the remainder as 0, which meant the HCF of these two numbers is nothing but 196. What most of the people will be doing as a mistake is, once 196 ka subtraction is done, 196 I start dividing it with 196. No, you have to make sure whatever are the digits that are present in the dividend should be taken into consideration while doing the division. If they are not completed, you have to make sure to take them down and perform the division. Only once all the digits of dividend are done, you should be considering the divisor to divide with the remainder. Alright. So what is the HCF of these two numbers? That is the whole point of me explaining the second problem. Because most of the people will be getting confused here. Okay. Is nothing but 196 itself. Now that I have solved first bit and second bit, I'll leave the third bit to you guys to simplify. Alright, let's get started with the second problem. Here we are with the second problem. Use division algorithm to show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. Alright, let's get to the solution. Here they are saying that any positive integer is of the form, let some number which is dividend, our dividend, capital N is equal to 6q plus 1. Okay, when we are saying that this is in the form of cq plus r, c is equal to dq plus r, right? This is in the form of our Euclid's lemma. C is equal to dq plus r, right? Where, what is the divisor here? D is equal to 6. Now, when we get to know that divisor is 6, according to Euclid's lemma, what did he say? He said the remainder should be either equal to 0 and it should be less than d, less than remainder. So what does this n become when we divide something with 6q? What should be the remainder? It can be 6q plus 1. First thing is 6q plus 0. Next 6q plus 1, 6q plus 2, 6q plus 3, 6q plus 4 and 6q plus 5. Can we write 6q plus 6? No, because remainder should always be less than divisor. So these are all the values that we get when we divide something with number 6. Okay, when divisor is 6, the remainder can vary from 6 to 5. Now what are they asking us? To show that any positive odd integer, what do you mean by odd? Which should not be divisible by 2. Isn't it? Now consider this 6q. Can I write 6q as 2 into 3q? 6q plus 1 I cannot write, and 6q plus 2 could be written as 3 into q plus 1, and 6q plus 4 2 into 3q plus 2, and this cannot be divided by 3. So these three values are not divided by 2. So in order to be odd, the values should not be divided by 2. So for the values 6q plus 2 and 6q plus 4, they are divisible by 2. Hence they are not odd, right? Hence they are not odd, they are even. So what are they asking us? They are asking us odd integers. So what are the odd integers which are not even, which are remaining? Hence 6q plus 1, 6q plus 3, 6q plus 5 are nothing but the positive odd integers. Is that what they are asking us? Yes, to show that any positive odd integer is of the form 6q plus 1, 6q plus 3 and 6q plus 5. Hence proved. But make sure to hence write this statement, okay? Hence any positive odd integer is of the form 6q plus 1, 6q plus 3 and 6q plus 5. Alright, so this is about problem number 2. Let's jump into the next problem. Yeah, here we are with the third problem. Use division algorithm to show that the square of any positive integer is of the form 3p and 3p plus 1. So for us, let us assume the dividend to be, okay, say for suppose 3p. What does this mean? It means that the divisor is 3p. According to Euclid's lemma, when divisor nothing but d is equal to 3, what are the possible outcomes of n? 0 less than or equal to r less than d, right? So remainder should be less than d. So till 3p plus 0, 3p plus 1, 3p plus 2. So n becomes these three values, right? 3p plus 3 cannot be because it should be less than the divisor, which is 3. Now, what are they asking us? Square of any positive integer. Let's apply square for this. 3p whole square is what? 9p square. Alright, now 3p plus 1 whole square is nothing but 9p square, a plus b whole square expansion. 1 plus 2 3 is a 6p. And 3p plus 2 whole square, the square of this, is equal to 9p square plus 4 plus 2 3s are 6, 6 2s are 12p. What I have done, I just have applied the a plus b whole square formula here. Now 9p square, can it be written as 3 into 3p square? Because they are asking to show that it should be in the form of 3p or 3p plus 1. Okay, now if I take 3 common here, p square, 3p square plus 2p, 3 2s are plus 1. Okay, now this can be written as 3 into 3p square plus 4p plus 1 plus 1. Okay, let me explain this in detail. So I just have taken, this can be expressed in the form of 3p. So 3 I have taken common and this is 3p square. Now here among these two terms 9p square plus 6p, I have taken 3 common. That becomes multiplied with 3p square plus 2p and plus 1 as it is. Now among these two 9p square plus 12p, I have written 4 as 3 plus 1. Okay, so 3 when I took common, 3p square plus 4p plus 1 is 3 plus 1 is 4. So now can I consider, now let me assume this as p. What does this become? 3p. If I assume this as p, this becomes 3p plus 1. When I assume this becomes p, this is also in the form of 3p plus 1. Isn't it? So the square of any positive integer is of the form 3p and 3p plus 1. Hence proved. Alright. This is about the problem number 3. The problem number 3 is here I have taken the square of the positive integer. Next one is cube of the integer. So since I have solved this, I'll leave it to you guys to solve this. If you do not get it, let me know. We will solve it in the later videos. Alright, let's jump into problem number 5. So here we are at problem number 5. Show that one and only one out of n plus 2, n plus 4 is divisible by 3 where n is any positive integer. Alright, so for us they have given n plus 2 and n plus 4. Okay, so let us consider for n is equal to 1. So here we have problem number 5. Show that one and only one out of n plus 2, n plus 4 is divisible by 3 where n is any positive integer. They are saying it as positive integers. When we are discussing about integers, any values from 1 after 0, we thought they are positive integers, right? So given values are n, n plus 2 and n plus 4. So let me take n as 1. For n is equal to 1, what does n become? N is equal to 1. n plus 2 is 1 plus 2 is equal to 3. n plus 4 is 1 plus 4 is equal to 5. So for n is equal to 1, what is divisible by 3? n plus 2 is divisible by 3. Okay, for n is equal to 2. So n plus 2 becomes 2 plus 2 is 4, which is not divisible by 3. n plus 4. 2 plus 4 is equal to 6, which is divisible by 3. So here n plus 4 is divisible by 3. Alright, let's consider n is equal to 3. n plus 2 becomes 3 plus 2 is equal to 5. And n plus 4 becomes 3 plus 4 is equal to 7. Now, among these three values, which is divisible by 3? N, right? So this implies n is divisible by 3. So here, now whatever the values that we have taken 1, 2 and 3, when we have substituted only one value, which is n plus 2 is divisible by 3. When we have substituted 2, only one value, which is n plus 4 is divisible by 3. And when we substituted 3, we got a value n which is divisible by 3. So in none of the cases, when I substituted 1, n plus 2. But when I substituted 2, is it n plus 2? No, n plus 4. But when I substituted n is equal to 3, is it n plus 4 again? No, it is n. So that is what they are asking us to prove. One and only one out of these three values is divisible by 3 where n is any positive integer. Now that we have substituted the positive integer values, out of which only one and only one value is divisible by 3, isn't it? Is that what we have proved? Yes, right? Now, hence proved. They are just asking us to show us among these three values at a time only one value is divisible by 3. So, congratulations, we have completed exercise 1.1 in chapter 1, real numbers. So, this is about the first video of real numbers. If you like the content and you are able to understand this, please do like and also share with your classmates or in your relatives. If anybody is studying in 10th standard, please forward them to these videos to them as well. And please don't forget to subscribe to Untitled Academy so that whenever I upload a next videos as part of the continuation to these things, you will get notified and you can go through them as well. Thank you for watching.